So let me start by thanking the organizers and all participants really for putting together this wonderful conference. This is a review talk. I try to be thorough in my referencing, but I'm sure I missed all kinds of interesting work. So feel free to add any references to the Slack thread related to this talk. So I'd like to start with putting up this rather simplistic picture of what the first giga year of the universe roughly looks like, at least in my mind. And that is that any kind of structure that we're interested in ultimately starts with a cosmic overdensity on some scale. If it's a large scale overdensity, then such a region will become a galaxy cluster. More modest overdensities will form the first galaxies. And if it's a really high overdensity on an extremely small scale, then this will form supermassive black holes that we need to power quasars. And we also know that all these types of structures have some contribution to reionization. And since we're here talking about structures that are some of the first structures to form in the universe, they're bound to create early reionized regions in the universe. And we also know that we need some kind of seeding mechanism for the supermassive black holes. Whether your favorite black hole seed formation scenario are population 3 stars or more massive direct collapse black holes, these formation scenarios are also closely connected to cosmic overdensities. So in the first part of this review, I will walk this upper path relating overdensities to galaxy clusters and a little bit of reionization. And then in the second part, I will walk this this path related to the black hole, so that we can really try to compare the two. Now, theory tells us that galaxies in the most massive dark matter halos today formed their stars at very high redshifts on average. And if you focus on today's massive clusters, let's say halos of 10 to the 14 to 10 to the 15 solar masses, most of their action is over by the time you get to redshift 2. So this figure here from Overzier all shows very nicely that the peak star formation epoch for the galaxies that make up these kind of structures today happens at redshift 3, 4, 5, etc. So that's theory. And we also see this if we look at some rather extreme examples of galaxy clusters that have been found at very high redshifts. So here example redshift 1.2, redshift 1.8, and redshift 1.98. And these particular clusters, despite their high redshifts, they already have a lot of the features that we know and love about galaxy clusters, such as a thermalized ICM and a very high fraction of passive and early type galaxies. In particular, the cluster at redshift 1.98, the estimated formation redshift of the stars that make up the passive population in this cluster, according to Willis et al. 2020, should be placed somewhere around redshift 10. In other words, long before this object became a cluster. Currently, the most distant cluster discovered is probably this one at a redshift of 2.5. In the cosmos field, there is a large agglomerate of structures between redshift 2.4 and 2.5 that is referred to as Hyperion. And the largest substructure within this structure is this object here that has an X-ray luminosity of 10 to the 44 erg per second, possibly a virialized mass of 10 to the 14 solar masses. It would evolve into a 10 to the 15 solar mass cluster by the present day. However, we need to be a little bit cautious with the interpretation of this X-ray structure, because the structure contains several radio AGN. So there is some ambiguity here. Nonetheless, it's a very old, impressive, massive structure. This figure here summarizes what especially Sunyaev-Sadovitz surveys have contributed to the field of cluster evolution. Planck, SPT, and ACT have drastically increased the sample of galaxy clusters out to redshift about 2. But it also shows you the limit of these techniques. And we essentially failed to go much beyond redshift 2, not only because of technical reasons, but mostly because of astrophysical reasons. And that is because if you look at the typical growth of, let's say, a massive cluster like a coma or proto-coma cluster in this case, and you look when such an object first passes this magical 10 to the 14 solar mass threshold that we use to define clusters, then this happens to a redshift of about 2. So we do not expect any clusters or highly massive dark matter halos much beyond redshift 2. So does that mean that the study of cluster formation or evolution ends there at redshift 2? Well, no. So if we all put on our dark matter glasses for a minute and we look up to the sky, we would actually very easily be able to pick out the regions where massive objects are forming. And you can see this by comparing these two snapshots from the Millennium 2 simulation, redshift 6 and redshift 0, showing you 3 different scales. If we could see the dark matter, it would be quite easy to point out where we believe the clusters are forming. Now, I don't have dark matter glasses, but mixed in with the dark matter, there would be gas and galaxies, and those we can try to detect. Again, this works in theory and in simulations. We see there very clearly that higher mass clusters today generally came from larger overdensities of gas and galaxies. And we can try to detect those, and we can even predict some interesting physical parameters like a present-day cluster mass from a galaxy overdensity or a gas overdensity measured at very high redshifts. And so in principle, this would allow us to follow cluster evolution way beyond redshift 2, perhaps all the way into the epoch of reionization. So that theory, does it work in practice? It does. Cluster progenitor systems have been found out to very high redshifts. And these systems, they generally satisfy the properties that we expect for the protocluster stage of clusters, again, according to simulations. And here I show you 2 examples. These were some of the first structures discovered. The so-called spider web protocluster at redshift 2.2 and the SSA22 structure at redshift 3. Despite the redshift of the SSA22 being higher than that of the spider web, it seems that the SSA22 structure is actually much more impressive structure, a progenitor of a very massive cluster. So in the last 2 decades or so, maybe 30 or 40 of such systems have been found in all kinds of ways by targeting quasars, radio galaxies, or serendipitously in the field. And in the past 5 years, I would say that this has completely changed. And we now have samples of hundreds to even thousands of candidates of such structures, largely thanks due to the very wide and deep surveys on 8-meter telescopes. And actually the main limiting factor at this moment seems to be the spectroscopic follow-up to confirm all these large numbers of candidates. And some of the projects and surveys that have been particularly helpful in this explosion of interesting structures at high redshift are the Carla project, which was a project to target radio loud objects at high redshift and look for their environments. The Hyper Supreme Cam systematic survey in broad and narrow bands that I highlighted here. And also a very nice surprise has been the discovery of these massive systems in surveys with Planck, South Pole Telescope, and Herschel. So I'll highlight some new developments or recent developments in this area. One of these, as I mentioned, is the Subaru Hyper Supreme Cam systematic survey, and in particular the wide survey allowed us to select 200 candidates of these systems at Redshift 4 using only 10% of the initial survey data. And we believe that these systems have the properties typical of sort of intermediate mass clusters today. And if you have such a large number of candidate systems, that means you can make all kinds of interesting stacks and statistical exercises that we couldn't do before, such as this result by Mariko Kubo et al. 2019 that show that these UV selected Redshift 4 systems are detected in a deep stack of Planck data. And so this shows that despite their UV selection, there's probably also a large obscured star formation rate with some AGN activity mixed in these systems at Redshift 4. Now, another very positive addition to this field has been the dense spectroscopic field surveys, such as the VMOS ultra deep survey, VUDS. And this project showed that if you take densely sampled spectra on some sky region, then you're also able to find these kind of structures in redshift space without necessarily being able to detect them in terms of a surface overdensity in a sky plot, as shown here in these two figures. And then a third very interesting addition to this area of research has been the IGM tomography studies, such as the Mammoth, Clamato, and Lattice projects. And this has really opened the door to not use galaxies to select these kind of structures, but to go after the gas overdensities. And in this case, these structures are discovered through the absorption features that they imprint on the spectra of background quasars and galaxies. And within a couple of years, we'll have two new instruments, VLT Moons and Subaru PFS, that will be absolutely fantastic to combine all of these search techniques over very large areas in a systematic way. Another very interesting development has been the realization that we can use CMB and SZ surveys to look for these overdensities of obscured star-forming galaxies, which leads to so-called cold spots in CMB data. And here I show two quite spectacular examples of systems with Redshift 4 and 4.3 that have received a lot of attention in recent years. These structures appear to be far infrared bright, but UV dark. So perhaps they are complementary to our UV selection. In both cases here, there is a large number of galaxies on rather compact scales of maybe a few hundred kiloparsecs, leading people to believe that perhaps we're seeing here the proto-BCGs. And on large scales, these systems appear to be rather overdense and massive, leading to the conclusion that perhaps these are super coma clusters in formation, as you can see here in this overview produced by Long et al. 2020. Now we finally get to the first billion years, which is the point where I wanted to get to. So in theory, we can extend this kind of search for cluster progenitors all the way into the epoch of reionization. In this work from Chang et al. 2017, it is shown that actually, since these systems are so biased, they form rather early. They contain large numbers of star-forming galaxies distributed over large co-moving volumes. And that means that they actually make a non-negligible contribution to the overall cosmic star formation rate density. And based on the simulation, perhaps they could contribute as much as 50% of the cosmic star formation rate density by the time you get to redshift 10. And so these kind of structures could be major sources of in particular, the early reionization. And maybe if we had maps that show the topology of the reionization process, this could be dominated by these very large bubbles surrounding these first major structures. Again, this is all theory. Does it work in practice? Well, actually, we have many examples now of such structures, mostly composed of Lyman break galaxies, Lyman alpha emitters at redshift 6 to 7. This morning we saw the talk by Wei-Da Hu giving an example at redshift 7.1. And so there's certainly no lack of rather rich structures that we can detect. Actually, with quite modest means, using dropout surveys, Lyman alpha narrowbands, followed by spectroscopy. And these are some of the best examples that I know of, but there are others. And we've also heard during this this conference that things like double peak Lyman alpha emission or enhanced Lyman alpha transmissivity may be smoking guns of large-scale ionized bubbles. And if that is true, then perhaps we may expect that in and around these first examples of overdense regions, such tracers of reionization will be detected in the coming years and at a rate that is more common or higher than around typical field galaxies at a similar redshift. And there are several observational papers that I have referenced here below that seem to go in toward this direction with indications that there might be observational signatures of these first large overdense regions. Okay, now we finally get to the quasars. So we have heard many times during this conference that theory and simulations consistently predict that the first quasars form in early overdense regions. And we've seen evidence that some quasars indeed appear to be in rather complex or dense environments. However, as I will show and others have shown, this does not appear to be the case for the population of the first quasars in general, given the current observational evidence. And this becomes particularly striking when we compare these objects with the other massive structures known at redshift 6 to 7 that I have just showed you. So let's start with making a very quick summary of what we think we know about the redshift 6 quasar population. The typical black hole masses are 1 to a few times 10 to the 9 solar masses. Dynamical mass estimates suggest that the mass to black hole mass ratio is about 7 times below the local M sigma relation. So this is one of the methods that we can use to try to infer dark matter halo mass. I know of at least 4 or 5 more or less independent means of estimating the halo mass of these redshift 6 and 7 quasars, using proximity zones, arguments based on number density, direct comparison with simulations. And I think these all point to halo masses of around 10 to the 12 to the 12.5 solar masses. We've also seen that some quasars require superhuman growth, in particular the more massive black holes above redshift 7. And what I mean by superhuman is that no human can currently explain the formation of these objects without invoking some kind of exotic scenario that gives us, for example, a 1,000 solar mass black hole at a redshift of 50 that then also needs to accrete continuously at the Eddington rate. And we also know that 10 to the 15 solar mass clusters today typically had a halo mass or had a halo with a mass of somewhere around 10 to the 12 solar masses way back in their merger history, somewhere around redshift 6. So the naive expectation of all of this is that the quasar environments at redshift 6 and above should be incredibly rich. So let's ask if they are. I've taken this list from a paper by Chiara Mazzucchelli from 2017, and I added more recent papers. Faiga Wang showed a similar overview with sort of a classification of whether these particular quasars show evidence for overdensities or not. And I'm actually going to take a little bit more conservative approach than Faiga Wang did, and that is only allowing spectroscopic evidence for overdensities. Okay, and the reason for this is twofold. We have seen many times in the past that photometric overdensities of dropouts later were shown to be projection effects after doing spectroscopy. But also all the protocluster systems that I showed you that we know of at redshift 6 and 7, they have all been confirmed spectroscopically. Okay, so so if we do that, then this list looks rather sad. If we had made this list 2 years ago, we would have answered no everywhere. Recently, there have been a number of very interesting papers that we've also seen already appearing in this conference, presenting evidence for overdensities on some scale with some selection method for at least a number of quasars, but certainly it seems to be the minority at this point. One of these is this object, 0836 at redshift 5.8, discovered by Xiaoyi Fan et al. 2001. It has a black hole mass of about 3 × 10⁹ solar masses. This object formed one of the chapters of my PhD thesis 15 years ago, and we presented there a photometric overdensity of 7 dropouts. I've been highly skeptical of that result for 15 years because of the lack of spectroscopic confirmation, as I mentioned, until about a year ago when a very interesting paper appeared led by Sarah Bosman that obtained 3 redshifts of galaxies close to the quasar, 2 of which are coinciding with the dropout galaxies. One of these objects, which is Galaxy A, is actually detected with Spitzer at 3.6 micron, which we already knew in 2009 when we obtained the Spitzer data, but we didn't have a redshift, so we couldn't make too much of it. But now we know that this means that this is an object with a stellar mass of a few times 10 to the 10. The inferred halo mass would be 10 to the 12 solar masses, and that would suggest that this field does not contain just one massive 10 to the 12 solar mass halo associated with the quasar, but at least one more associated with one of these galaxies. And this requires an overdensity of on this scale and of this type of halos of about 20. Another interesting object, which curiously enough was also from the sample of 3 objects discovered by Fan et al. In 2001. This is a quasar redshift 6.3. We have seen this figure several times already during the conference. In this case, there are six spectroscopically confirmed galaxies. And although these 2 fields differ in the details, I would actually argue that actually on scales of about 5 proper megaparsec radius from the quasar, they are quite similar, as shown by these 2 projections here. Now, there are other interesting environmental finds that we have also seen presented during this conference, such as the companions, very close by massive companions detected in C2, or the recent result of a first binary quasar at redshift 5.7 by Yu et al. And so this could either reflect maybe the duty cycle of typical merging activity in a rather uniform quasar population, but perhaps it could also be an indication that the redshift 6 quasar population is more pluriform than previously thought. And that perhaps could explain some of these very striking differences. Now, the reason why I showed you all this evidence on non-quasar related overdensities at redshift 6 and 7 is because now we can then compare what has been found around the quasars to these other so-called protoclusters. And what we then find is that perhaps the structures as found, for example, around these 2 quasars, 0836 and 1030, they resemble sort of the densest peaks that you find inside these redshift 6 to 7 protoclusters, but they appear to lack the large-scale structures that are typical only of these protoclusters. And I think this is a very interesting clue, perhaps, to what is happening.
5 minutes.
So, thank you. So let's look at some possible solutions or explanations that could be consistent with these data. So the first often heard conclusion is that the quasars are in dense environments, but for some reason, we are not detecting these environments. And so the main problems to me is that this would imply a rather strange luminosity function for galaxies in the vicinity of the QSO, but actually out to tens of megaparsecs. And it is also conflicting with the overwhelming evidence of very large overdense structures in the field that were quite easily found, as I have shown you. So another common explanation is that the quasars are in dense environments, but photoheating has suppressed star formation. And the main problems here I see is that actually the best evidence for companions of quasars today is on very small scales and not on large scales. It would also require that this photoheating is efficient out to many megaparsecs, uniformly over 4 pi steradian, and also that the quasar duty cycle needs to be close to 1 in order to continuously suppress any Lyman alpha or Lyman break, Lyman alpha emitter or Lyman break galaxy formation over very long time scales. And actually, one of the results from the paper by Sarah Bosman et al. Shown here in this in the bottom right is this object found very close to the quasar redshift 5.8, which shows very bright double peak Lyman alpha emission. So clearly, this galaxy was able to form within the ionization cone of the quasar. But what's more, the ionized region actually allowed this double peaked, this very strong double peak Lyman alpha emission to emerge. And so, if anything, this quasar ionization makes it easier to spot these objects. And so, these two particular explanations have never been very convincing to me. And a third option here that I'd like to maybe put back on the table is that the quasars might be in dense local environments, but not necessarily the largest, the most massive, the most extreme overdensities that we usually associate them with. And I'd like to bring back to your memories these results from already 10 years ago. And that is, if we look at the merger history of massive clusters selected at redshift 0, then those objects are likely to include 10 to the 12 or more massive solar mass halos at redshift 6. But that's not the experiment we're doing here when we're selecting quasars, okay? So if we look at what are the typical descendants of 10 to the 12 solar mass halos selected at redshift 6, then their descendants at redshift 0 are much more diverse, spanning maybe 2 orders of magnitude between 10 to the 13 and 10 to the 15 solar masses. No doubt massive structures, but certainly not necessarily the largest. And there's another interesting paper here shown on the right from Angulo et al. 2012 that actually shows you that it is the large scale environment, scales of tens of co-moving megaparsecs, that is most indicative of the future growth potential of a structure selected at redshift 6. And in these particular simulations, if you select the most massive object at redshift 6, it does not become the most massive object at redshift 0. On average, actually it becomes less massive than structures that are not as impressive yet at redshift 6. Now, the final topic I'd like to reach here is related to the seeds of the first supermassive black holes. So this question of environment has direct relevance to many of the black hole seed formation and growth scenarios proposed. The direct collapsed black hole seeds have been postulated in order to explain the supermassive black holes above redshift 7, but they have never been detected, and we don't know whether a viable formation scenario exists. According to the theory for the formation of these very massive seeds, we need a combination of an enhanced local UV photon background together with high merger rates of mini halos. And interestingly, these are predicted to primarily occur in very large overdensities above redshift 10. So quasars like 08936 and 1030 could be good examples of regions in the early universe where such direct collapsed black hole formation was stimulated. And I would expect that quasars like ULAS 1342 at redshift 7.5 may show similar results. This is my final slide. Faiga Wang already presented to you a very interesting overview of all the interesting JWST programs that are going to address these issues related to quasar environments. I'd like to add to that several programs in GEO and GTO time that will target radio loud galaxies between redshift 4 and 6, and it will offer us a very interesting comparison in terms of the host galaxies and environments with the quasars. Moons and PFS will soon begin to systematically study large-scale environments. And I'd also like to mention that instruments proposed for GMT and ELT are actually very well matched to the typical structure sizes of what we need to do this really, really well spectroscopically. And I think I'll conclude here. There are some other ways in which in the coming years we will learn a lot more about black hole demographics that will maybe help us to at least indirectly infer much more about the seed population, if not detecting them directly. Thank you very much.
Thank you for a very informative talk. So we have one question up on the Q&A from Sheila Kanapan. Is the mix of environments for quasars statistically consistent with random environments?
I think that could very well be, yes. Of course, the other side of the coin is that the 3 or 4 objects that have, several confirmed companions nearby, I think that this is quite spectacular. Even confirming a small number of Lyman alpha emitters at the same redshift as the quasars. This is not something that you see in typical, let's say, field environments. But yeah, I personally believe it's quite possible that we're seeing a very large mix of environments, which probably is no longer true by the time you get to redshift 4. Yeah, I agree with that.
Okay, great. Are there any other questions? There's no other open questions on the Q&A. So while we're waiting for that, maybe this is not my field, but I'll ask you a sort of general question. What do you think is the most pressing open problem in this field today that can be addressed today? How about, and we don't have to wait for any new machines.
Well,
Okay.
until you added the last sentence, I would say I would be really interested in finally knowing what's the seed population. I think this this is the elephant in the room. Knowing whether we have to start from population tree seeds or from much more massive seeds would create enormous clarity by discarding a whole family of models. And this is what I would really like to know. I'm hopeful that maybe not now, but within the next 2 years, especially the many JWST programs, we will learn a lot more about this.
Okay. We have a question from Darren Croton. Didn't we just see that higher Z quasars were much more clustered, so not random?
Yes, so I should maybe stress that what I presented here really refers to the redshift 6 and higher quasar population. We have not measured a correlation function for quasars or redshifts at these redshifts. And so I agree with most of or everything that Christina presented this morning. But all those constraints on clustering, cross-clustering, all comes from redshifts 4 and lower.
Great, we still have time. So we have another question from Michael Strauss. We heard intriguing evidence in earlier talks that overdensities around Z equals 6 quasars were more prominent in obscured galaxies than in unobscured quasars. Do you find this convincing? How does that fit within your scenario?
So thank you very much, Michael. I was expecting this question. So of course we often make the argument that somehow we are convinced that the massive structures are there, but we are not detecting them therefore all these galaxies are obscured. Okay, it is certainly possible, but I don't find it a very convincing argument. It sounds a little bit to me as the epicycles. Now, if this were at Redshift 4, I would certainly, I would have no problem with this. And I've shown you examples of these massive protoclusters that are primarily seen in a dust obscured way, lacking many UV of any UV galaxies, UV selected galaxies, Lyman alpha galaxies. Above Redshift 6, I'm not convinced. I find it too easy to say, well, the structures must be there. We're just not seeing them, just in order to hang on to our strong conviction that these quasars must be in the most overdense regions of the universe. I'm happy to be proven wrong, but I don't think we have, there's convincing information to take this as our explanation. So,
Okay, so we have another question by George Gonzalez Lopez. If the QSOs do not live in the largest overdensity structures, should we be looking for other sources such as sub-millimeter galaxies at Z greater than 6 to find the most massive halos?
So that's a good question. So that allows me to say it a little bit more clearly. I do believe that the quasars are in very massive halos, possibly the most massive halos that you find at Redshift 6. But these are not necessarily in the largest overdensities on tens of megaparsec scales. So maybe it is possible that by selecting these very early collapsed objects, such as the supermassive black holes and the quasar hosts, we are sort of biasing ourselves to overdensities that were very large on small scales, not necessarily on large scales.
And there was an addendum to Michael Strauss's question. Sorry, I mistyped. Unobscured quasars should be unobscured galaxies. So that was what he was thinking, rather than quasars. Oh, I lost the question. I'm not sure where it is. Here it is. But still a couple minutes. Anybody have another question? I guess I will ask another vague question. So what are you currently working on? What is currently the most exciting project you're working on?
Good question. One thing I'm really intrigued by is the role that these overdense structures can play in the early reionization process, and whether this can be detected rather than saying, look, we find a large overdensity of galaxies at some redshift, and therefore probably this region reionized early. It would be really nice to be able to show this observationally, and I think there are ways in which this can be done very soon by measuring, for example, the escape fraction of Lyman continuum photons coming from these regions, and compare this to galaxies in the field.
Okay, let's see. I don't know if this can be done in a minute, which is all we have left. Perhaps so. Reversing the argument, what is your idea regarding not detecting AGN QSOs in, for example, the many serendipitously found Z 6 to 7 overdensities of galaxies you summarized?
Yeah, that's another good point. I should have said that, as far as I know, none of these structures contain luminous quasars. Of course, it is possible they contain obscured quasars, or there are supermassive black holes, but they're currently not actively shining. So I don't see this as a problem. It is easy to switch off a quasar in a large-scale structure at some moment in time. However, it is impossible to switch off the large-scale structure around an object that is currently a quasar. And so I think there's a lot of information in this kind of comparison.